Hi, we are presenting multi-manifold learning for large-scale targeted advertising system with Kyung, Youngjin, Kyungmin, Sunyoung. First, introduction. Messenger advertisement give direct and personal user experience, adding high conversion rates and sales. However, people are skeptical about ads and sometimes perceive them as spam, which eventually leads to a decrease in user satisfaction. The key to the success of a precise user targeting lies in running the accurate user and ad representation in the embedding space. Existing methodologies implicitly embed the entities into points in Euclidean space, which cause an inherent limitation in the representation power. The latest studies, however, pointed out that the real-world user-item interaction dataset exhibits the hierarchical structures. Thus, we propose a framework that can effectively learn the hierarchical structure in users and ads on the hyperbolic space and extend it to the multi-manifold learning. What is hyperbolic space and why is a hyperbolic manifold well-suited space for hierarchical structure? Hyperbolic space is a non-Euclidean space with a constant negative Gaussian curvature. Hyperbolic space is often associated with Minkowski spacetime in special relativity, which points are represented on the virtual icon of a two-sheeted hyperboloid of n plus one dimensional Minkowski space as shown in figure 2. The hyperbolic manifold is often considered as well-suited space for hierarchical structure. Suppose a task that embeds a tree into the metric space while preserving its structural properties. Then Euclidean space cannot contain all the nodes in the tree, which leads to poor representation of the model. However, in the hyperbolic space, the circle length grows exponentially with the radius, enough to include all the nodes. Figure 3, M-Scioscia-style illustration of the Poincare disk model. Each triangle has constant area in hyperbolic space, but in Euclidean space, it rapidly shrinks at the boundary. In this section, we are going to cover basic formulation of targeted advertising system. Unlike the traditional forms of advertising that expose ads to random users, the core of targeted advertising is that the system sends ads to different user groups based on the user ad preference. So the targeted advertising system uses the site information of those ads, such as image and advertising phrase, as well as the user's demographic information and click history to find the most relevant user group. X denotes input features of ads and users, and F denotes MLP layer that transforming input features X to embedding vector Z. And history embedding layer F sub H can be transformer, LSTM, MLP, etc. Finally, the preference score P between the users and ads are computed through the distance or inner product between embeddings of them. Next, we will briefly cover hyperbolic geometry. First, transition map. Exponential map is a map from points of tangent space to Riemannian manifold. In this case, hyperbolic space. Intuitively speaking, the exponential map takes a given tangent vector to the manifold, runs along the geodesic starting at that point and goes in that direction for a unit time. Logarithm map is inverse of exponential maps. Next, diffeomorphism. Diffeomorphism maps one differentiable manifold to another such that both the function and its inverse are smooth. In this case, hyperboloid and Poincare disk. The hyperbolic model tends to be more robust and stable than the Poincare model, but the Poincare model is easier to interpret and can visualize embeddings directly on the Poincare disk. Right figure shows how diffeomorphism works in the hyperbolic model. Our proposed method, multi-manifold learning. Although the hyperbolic space has successfully reflected the topology in user item representation, the existing approaches fix its origin and use single manifold as an embedding space. In a real-world, large-scale advertising system, there exist various groups of users with different preference characteristics, and it may not be valid to assume that every user and advertisement entity can be expressed by using single geometry, so we propose multi-manifold. This is a conceptual scheme of our proposed method: embedded users and ads into the same vector space using the previously mentioned embedding layer F, and then cluster them for each user. After clustering the users, we get the centroids that represent each user group. Based on these centroids, we build multiple manifolds using the centroid as an origin. Subsequently, we compute the distance between ad and user in each manifold, and we obtain the final preference score of the user and ad based on the calculation in multi-manifold. We denote C sub t as a centroid of tth group for t. Finally, these embeddings vectors map onto each tth hyperbolic manifold of which the origin is C sub t. Then we calculate the preference score on each manifold using a Fermi Dirac decoder and aggregate them. The detailed process can be formulated as follows, where probability between users and ads on each manifold is small p and user preference of whole manifolds are large P, that computed by summation of small p. Next, experimental result. Before we look at experimental result, we will go into details of dataset. Because of our large dataset, we randomly select 1 million users and split a dataset based on time. The first 14 days for training and the subsequent 2 days for test. For better representation of user and advertisement embeddings, age, render, mobile OS type, interest, number of line pay membership followers, and number of line pay membership follower attributes are used for users, while text and image are used for advertisement. The advertisement click history is used up to the date before the forecast date. Performance comparison. We report 3 accuracy metrics of ROCAUC, accuracy, and average precision, and 1 diversity metric of Shannon entropy. Average precision is set up for the targeted advertising system. The user preference is sorted for a specific advertisement, and then precision is calculated for each ad of the top K users. As shown in Table 1, our method shows the best prediction performance for all accuracy metrics as well as a diversity metric. The diversity metric of Shannon entropy for each model shows how diversified the recommended users are. Our model shows the highest diversity compared to other baselines, indicating that superior expressiveness of embedding enables precise targeting. To further demonstrate the effectiveness of our model on general data set, we present additional experimental result on public benchmark dataset movie lens. As represented in Table 2, our model shows the best or second best performance demonstrating its generality not overfit to the certain dataset. Effects of the number of clusters. Table 3 shows that the overall performance improves as the cluster grows, and the best performance is obtained at t equals 5. After t equals 5, the prediction accuracy converges while the diversity improves further. Embedding visualization. Figure 5 shows how multi-manifold learning works compared to others. From embedding visualization of MMP model and HNM model, we can verify their positive user pool responding to ads are very small. On the other hand, our proposed method, multi-manifold learning, shows that our model includes many users in a positive pool that is compatible with ads. The data embeddings in a different hyperboloid originating from centroid of different user groups have a different embedding space. Since we set 2 clusters, the figure 5 shows result for 2 manifolds. We can verify each manifold has a different distance in the hyperbolic space, as that are not relevant to the user are pushed to the edge, while preferred as appear to move toward the center. It is because the hyperbolic space we constructed is centered by the centroid of the well-clustered user group. Conclusion. Traditional targeted advertising systems struggle with the data representation capabilities because of the inherent limitation of Euclidean space. To tackle this issue, we present multi-manifold learning, a well-designed technique to learn better representation of users and advertisements. Experimental results show the proposed scheme improves the targeted advertising quality in terms of both accuracy and diversity. As the future direction, we will develop a multi-manifold learning scheme in terms of diffeomorphism learning. Thank you for listening, and please enjoy our full paper in QR code.